Okay, in this example, we've got a homogeneous bar which is attached to a shaft there at a vertical shaft. There's a moment which is acting on the shaft there of m, and as a result of this, there's going to be an angular acceleration of the bar as the bar moves in a horizontal plane. What we want to do is find the reaction force at R as a result of the applied couple there of m. So first thing I'm going to do is give some things names here. L is going to be the length of the bar, so it's 18 plus 12 divided by 12. So that's the length in feet as that. G is going to be at the midpoint here. So as I draw this in my FBD, this is G, and O is where the shaft is, and this distance from here to here, we're going to need that a little later on. The distance D is the halfway point. It looks like it's going to be 15 inches, so it looks like G is 3 inches to the left of so convert that to feet. Okay, so now let's do our FBD. FBD that I'm going to draw here is a top view. The reactions, Rx and Ry, that's acting at O, and then there's a couple, M, which is applied. Again, weight's not coming into the problem here because that's acting in the direction of shaft, and we don't see that force from this view. Our Newton-Euler equations. Summation of forces in X. I didn't say what X is, so X is going to be positive to the right. Y is in that direction. Rx, and that's equal to MAGX. Has to be the acceleration of the center of mass. Some forces in Y, we get Ry is equal to MAGY. In the moment equation, we could either use G or O. I'm going to choose O. The only thing that's causing a moment about O is our couple, applied couple there of M, and that's equal to the mass moment of inertia about O times the angular acceleration of the bar. But by choosing O, we need to use the parallel axis theorem to find out what IO is. So IG, recall, that's equal to 1/12 ml squared. So that's what we need to use for IO. This is just an application of the parallel axis theorem to take what we know about of the mass moment of inertia about G and find out what it is about O. So we can see here that we have equation 3 gives us a known value for alpha for the bar. Alpha is just m over IO. So that at this point is a known. It's plus, so that is counterclockwise as you would expect. But that doesn't tell us what AGX and AGY are. We need those to find RX and RY. So the kinematics that we need, what we'll do is relate the motion of G back to the pin motion of O. So AG is equal to AO plus alpha crossed R from O to G minus omega squared RG with respect to O. It says that it's released from rest with that applied torque, so omega is a 0. O is a pin joint or a shaft, so it doesn't move, so there's that. Alpha, we assume a plus sign here when we wrote down the moments about O, and the plus K. We'll have to do the same thing here. So that's alpha K. The vector which goes from O to G is a minus di. We know K cross I is a positive j, so it gives us minus d alpha j. So the point being that, therefore, from this we see that agx is a 0 and agy is equal to minus d times alpha. So we can now solve this, substitute our kinematics back into equation 1 when we find that Rx is a 0. And equation 2 gives us the important one, the y component. Ry is equal to m agy, so that's a minus d times alpha, and alpha was equal to m I o. So it's going to be a minus sign. So all this tells us is that the reaction force acting on the bar is going to be in the negative y direction as a result of that application of the couple there of M. So what do we do? Well, we drew an FBD of the bar. Only thing causing a moment about O was the couple M. So that right away tells us the angular acceleration of the bar. And then we use kinematics to relate the acceleration of G back to the alpha for the bar. We found out that the x component of acceleration of G is a 0. Acceleration of G and the y is a minus d alpha. Substitute that in, and we get the components of Rx and Ry.